I'm going to work through problem 4.7, but what I hope you'll see is we've actually already been doing what they're asking us to do in this problem already, which is to kind of show these tie lines, which I'm using because I want to show you that acid-base chemistry is really just a double displacement where we're swapping partners, but they're asking us to use arrows to kind of show how proton transfers occur. So I'm just going to kind of refer to these as tie lines, and we'll just do 2 more acid-base problems to just kind of practice that. All right, first problem here, hydroiodic acid. Again, chapter 2 is essential here to make sure that we're properly naming our acids. So hydroiodic acid, and again, we're drawing balance, total, net ionic equations here. So again, we're skipping that total ionic. It's actually only asking us for net ionic here. So we've got hydroiodic acid plus calcium hydroxide. Again, thinking about what changes places here, we're going to have new partners. So cations find new anions, and I can see here balancing, I'm going to have 2 hydroxides, so I better have 2 of my protons. I'm going to make 2 water molecules, and then calcium iodide. I need to refer to table 4.1, find out whether or not that's soluble. Turns out it is. That wasn't a problem like we just had there. Okay, so that's our balanced molecular equation. Again, total, we're going to mentally think about doing our total ionic equations. Okay, we already kind of showed our tie lines here to kind of show what happens. So if we think about then what is part of our net ionic equation, we're going to have 2 H pluses reacting with 2 OH minuses, and that gives us 2 waters. Right? I can see that iodide is aqueous on this side. It's going to be aqueous on this side. Calcium is aqueous on this side. Still aqueous on that side. So our spectators are calcium ions and then iodide anions. Okay, pretty straightforward. Nothing really fancy about that problem. Very similar to the ones that we just did in sample problem 4.6. Okay, working through this next one here. What's different? Oh, I forgot one problem here. This said, give the name and the formula of the salt present when the water evaporates. Okay, so when we evaporate the water, we're going to get this salt. We would call this calcium iodide. Right? If we now have this as a solid, not because it precipitates, but because we evaporate the water, this would be calcium iodide. Sorry, I forgot to answer that part of the problem. All right, now going to be, this problem is unique from the problems that we saw in problem 4.6 in that we have propionic acid. Propionic is a weak acid. And so in this problem, we're going to walk through and identify what we need to do when we have a weak acid in our ion equations. So potassium hydroxide, pretty straightforward there. And we have propionic acid. So just as an abbreviation, here's what I'm going to write for propionic acid. I'm going to write H, and then I'm going to write PR. Because I know that this is a monoprotic acid, I'm just going to show the 1 proton, and then this is the rest of the molecule that I'm just going to abbreviate PR. And why that's important is I don't want to have to rewrite all the atoms from that. Just to kind of have you know what propionic acid looks like, it's CH3, CH2, COOH, or if we were to kind of write all of our atoms together, it would be C3, let's see, H5, O2, and then there's our H. So remember for acetic acid, they kind of put all that stuff together. So this would be written as H, C3, H5, O2, and that identifies that that hydrogen is acidic. Okay, so we can write HPR, or we can write H with this. I'm going to write HPR just to kind of show you the simplified version. All right, aqueous. Show new partners. H goes with OH. K goes with our PR. So again, we're going to make H2O, and then K plus and PR minus, which again we could write as KPR aqueous. Okay, so what is different here, though? So this would be kind of our balanced molecular equation. When we write this as an ionic equation, we have to treat the fact that this is a weak acid uniquely. Okay, and so this is really important. This is kind of the different feature of this, is the fact that we are working with a weak acid. So mentally, we're going to kind of be splitting this apart. Potassium and potassium, aqueous, going to be a spectator ion. Hydroxides in our acid-base reactions are always going to be part of our net ionic, so there's my hydroxide. Here's how this problem becomes different. When we had a strong acid, we just wrote the H+. We're not going to do that here. This is a weak acid, which means it maintains staying together. It doesn't dissociate thoroughly, completely. So we're going to write this in its undissociated form in our ionic equation. So we write this what we call undissociated. Because it's a weak acid, we write it undissociated. We can still say that it's aqueous, okay? It's dissolved in solution. It's just not completely dissociated. It's not broken apart, okay? Now, we know we make water, right? Because that is the combination of the hydroxide and the water. But when we take that proton, when this hydroxide forcibly takes it away, what we're left behind is Pr minus, aqueous, okay? So truly the only spectator that we have for this problem is K+. Okay, so the net ionic equation is going to have all these species in. The only thing that it's not going to have is K+. And that's how we want to think about treating weak acids. Weak acids, when we draw them in our net ionic, remain undissociated. We don't break them apart. So for a strong acid, just to kind of flip back here and review, when we had a strong acid and a strong base, our net ionic equation was just H+ plus OH minus makes water. Another strong acid, strong base. We just have hydroxide plus H+ gives us water. When we have a weak acid, okay, we need to show the undissociated acid as part of our our net ionic equation. Hydroxide plus the undissociated acid, we're going to rip that proton off of our undissociated acid to make our water, and then that leaves behind the rest of that molecule.